In this video, we are going to see differentiation and the definition of differentiation and its meaning. Say, suppose we have a function f of x. The derivative of f of x, the derivative of f of x with respect to x, we denote it by f dash of x. Otherwise, differentiation of f with respect to x. The definition says f dash of x is equal to limit h approaching 0 or tends to 0 f of x plus h minus f of x divided by h. At any point x is equal to a, at any point x equal to a, we can define f dash of a in a similar way, like limit h approaches 0 f of a plus h minus f of a divided by h. Here h is approaching to 0. What is the meaning of entire definition? Let us check this with an geometrical view. For this purpose, I am explaining with the help of a parabola. So I am taking a function f of x is equal to x square. So now I am taking a function f of x is equal to x square. Here I am going to take a point A. So let me take a is equal to 1.5, and it is my choice. We can take any value. So we are taking here a is equal to 1.5. Let me mark a point on this parabola. So let me take a point A, where a is defined as a comma f of a. So we know a is 3 by 2, otherwise 1.5, and if we substitute 1.5 in the place of x here, we will get 2.25. So a is a point on the parabola. Let me take a value h. Here h is our limit value, which is going to approach 0. So I have just made that h is moving from left as well as right. So from right it moves, my right hand I have kept it as 2, and left hand I have kept it as minus 2. So from the left it approaches 0, and from the right also it approaches 0. So let us take that. Now let me take a dependent point B. Okay, so I am going to take a dependent point B anywhere here. Now suppose I have B to be defined as B is equal to a plus h comma f of a plus h. That is, x value is incremented by h, and f value automatically it is f of a plus h. So B is another point on the parabola, right? So when I change h value, then B will be moving, right? So when I change h value, the B moves towards A, or it goes away from A depending upon the h value. So we are making B as a dependent point with respect to the fixed point A. Now, we are actually talking about this point A. So, we are going to talk about what is happening to the tangent at any point on the parabola. So, let me take a tangent at a point A, where A is the point we are targeting. And let me see what is the line joining A and B. Now we have two lines. One is the tangent, one is the tangent at A, the other one is the line joining A and B, which is a secant. You can see it is a secant. So this is a line joining A and B. So when I move H, the point B will be moving towards A. So again, when H is on the right of 0, okay, so the point will be moving towards A from above. So it is moving towards A from above. When H is on the left, then we can notice that the point is moving towards A from downwards, right? So now let us check what is happening to the red line, that is the secant. The line joining A and B is a secant, and we know very easily, we can understand that as we move the point B, in order to move point B, we are actually moving H value, because B is a dependent point, and we know that B is being dependent with the help of H. So when we adjust the H value, B moves. And when B moves towards A, that is when H approaches 0, then we understand that the line is becoming the tangent at A, because B coincides with A. So now we can understand that the secant is becoming the tangent. So that means when B approaches A, the slope of the tangent AB, the slope of the secant AB will become the slope of the tangent. So when H is approaching 0, now we can see that the slope of the line is not defined, it is undefined. Why? Because if we go back to the definition, here we understand that H tends to 0, or when H takes the value 0, we have the division error. That is why it is undefined, and therefore we do not talk about what is happening when H is 0. We are only talking about what is happening when H is very close to 0. That is when H is very, very close to 0. So say H is equal to 0.005, what is happening? Okay, so if you have two lines, a line through 2 points A and B, point say A is x1 comma y1 and B is x2 comma y2, then slope of the line joining AB, otherwise slope of the secant, we know the formula is m is equal to y2 minus y1 divided by x2 minus x1. right? In our case, we have taken A as a point A comma f of A. So, and B is A plus h comma f of A plus h. So, when we talk about the slope of the line segment AB, it is m is equal to y2 or y2 minus y1. So, this can be taken as y2 comma x2. The first point can be taken as x1 comma y1. And when I talk about y2 minus y1, it means f of a plus h, f of a plus h minus f of a divided by a plus h is x2 minus x1 is a. So it is a plus h minus a. So this plus a and minus a cancels. So we have the slope of the secant AB is f of a plus h minus f of a divided by h. Whereas when h approaches 0, that means this point keeps moving towards A. That means at that point, when h is approaching 0, then B will coincide at A and this secant will become the tangent. So that is what we have seen in this animation. So you can once again notice that when we keep moving the h value, the secant is approaching the tangent. And notice that we are not able to give the slope of the tangent because h is equal to 0 here is undefined, whereas we can notice that the slope is 3, exactly 3 here. How it is 3? Y is equal to mx plus c. Here m value is 3, therefore the slope of the tangent is 3. And here we can see that equation of the line segment, if I change it to y is equal to mx plus c form, so let me change it to that form, right? So I am changing this to y is equal to mx plus c form. So now you can notice the slope of the line segment is 2.9. So when the h is equal to minus 0.1, then it is 2.9. When h is 0.2, say, it is 3.2. So we can understand the line's slope is 3.2. So when it is farther away, so when h is equal to 2, the slope of the line segment AB or the slope of the secant AB is 5 here. So when it is going closer to 0, it is, you can notice the value is reducing. The slope value here, you notice the slope value here, it is reducing. And you can notice that it is going towards, when h approaches 0, it is slowly reducing. And when it is almost close to 0, so let me stop here. Here h is 0.3 and you can notice that it is 3.3. Okay, and when h is 0.1, here you can notice it as 3.1. When h is 0.2 or 0.2, then h is, here the slope is 3.2. And when it is on the left hand side, the point is below A, and when h is equal to minus 0.9, that is left of 0, then we can notice that the slope of the line is 2.1 and it increases when it is moving towards 0, 2.4 it now, the value is 2.4, the slope is 2.4. And when I still move further, it is increasing, keeps on increasing. So it means the slope, when it is just close to 0, on the left it is 2.9, when it is just close to 0, on the right it is 3.1. So when the h is equal to 0.1, that is close to 0 on the right, it is 3.1. So it can be understood now that the value or the slope of the tangent at A now approaches 0. That is the point we are understanding here. So here when h approaches 0, now we can understand the two things. One is the secant AB becomes the tangent at A. So the slope of the secant is actually becomes the slope of the tangent, and we have understood the slope of the tangent is here is 3. Okay, 3 is the slope. Now let us go back and analyze the same thing. Let us now algebraically understand the derivative. So we had the function f of x. So f of x, what we have taken is x square, and when we are seeing the definition, we have two terms. One is f of a plus h, and the other one is f of a in the numerator. F of a plus h, in our case we have taken a to be 1.5. So let us use this 1.5 at the end. So when it is f of a plus h, it is a plus h whole square. Otherwise, if I expand this, it is a square plus twice ah plus h square, and f of a is a square. When I subtract f of a from f of a plus h, we will have this a square terms getting cancelled, and we will have 2ah plus h square. And when we divide this value by h, now on division of h, the right hand side becomes 2a plus h. When h approaches 0, so this term approaches 0, so we will have 2a, and we know a's value is 1.5. We have set it to be 1.5, which is 2 times 1.5, which is 3. So this is the value we got, the slope of the tangent at A. So this means that in order to define the slope of a tangent, we need to move the idea of finding out the slope of any secant where the secant's slope should converge to the slope at any given point on the parabola, which is the tangent. So this is one such an example where we can understand the derivative